Hi there, and welcome to the final lesson on trig identities and equations. So I'm going to wrap up this chapter by having a look at some very difficult questions involving use of the cast diagram, particularly question 6, the last worked example, which I've created myself to be particularly fiendish. So it probably, if anything, goes above and beyond the scope of the Year 12 course, but I figure I may as well put it in there just as a real challenge, just to see how you found it, and if you'd understand what we've applied and learnt so far. So first of all, have a look at these warm-up questions, 4 to have a go at. So attempt them first, then when you're ready to see the solutions, press play on the video again to see what I've got and compare it to your own solutions. Okay, so let's have a look together at question 1. So question 1 says, given that n is an even number, prove that 9n squared plus 6n has a factor of 12. So the first thing for this one is I'd suggest just saying that we can let n equal 2 lots of k, where k is a natural number. So k is a member of the set of natural numbers. This is just a mathematical way of saying k is a member of the natural numbers. K is any natural number, n equals 2k. So any even number is going to be a multiple of 2. So this is how we can define the even numbers. So even number implies it can be written in this form. So we can just take this expression here, 9n squared plus 6n, and substitute in the fact that we're setting n to be 2k. So that becomes 9 lots of 2k all squared plus 6 lots of 2k. 2k all squared is the same as 4k squared, and 6 lots of 2k is 12k. So if we expand this out, 9 multiplied by 4k squared is 36k squared plus 12k as before, and 36 and 12 have a common factor of 12, so we can factorise out the 12 here. We could actually factorise out the k, but we need to just emphasise that the factor of 12 is the one we're after. So we can say it's 12 lots of 3k squared plus k. So because we can literally factorise out the 12, this is the same as saying that 12 is a factor of this expression. So i.e. 12 is a factor of the initial expression we were asked about in the question. So 12 is a factor of 9n squared plus 6n when n is even. And that's all there is to that one. So let's have a look at question 2. Question 2, you have a curve y equals root x is translated onto the curve y equals the square root of x minus 4. And this translation is described by a column vector, so we just need to circle the correct vector that describes this translation. And so if we think about this in terms of transformations of functions, we can let this be f of x. So y equals f of x. So the input, x, just is square rooted. Here, the input isn't x, it's changed from being an input of x to an input of x minus 4. So before, only x was being square rooted. Now, for this one, x minus 4 is being square rooted. So what sort of translation would take f of x and transform it into f of x minus 4? Well, this is the type of question I've explained in the past a few times. The change here has happened from within these brackets around the x. So when the change happens from inside the brackets, if you like, colloquially speaking, the change affects the x values in an opposite common sense way. And so rather than subtracting 4 from each x value, what actually happens here is we add 4 to each x value. And so this means it's going to be a translation that moves the x-coordinates 4 to the right, not 4 to the left like you might think. And we don't move up or down because the y-coordinates aren't affected, it's just the x values which are. And so the one we need to circle is this column vector here, 4, 0. Question 3, we have a circle with equation x minus 4 all squared plus y plus 4 all squared equals 9. We just ask simply what is the area of the circle. Give your answer in terms of pi. We need to remember, and just know this off by heart really, that this is the equation of a general circle, and the constants inside of these brackets tell us the coordinates of the centre of the circle. And so essentially what this means is it's a circle. The centre, the x-coordinate of the centre is this value here multiplied by minus 1. So x minus 4 means the x-coordinate at the centre is positive 4. Because we have y plus 4, this means that the y-coordinate at the centre is actually minus 4. And the radius is given by this constant term at the end square rooted. So we square root this to get the radius. So the radius is basically the square root of 9, which obviously is 3. So therefore the area of this circle is pi r squared, obviously. So pi multiplied by 3 squared, which is pi multiplied by 9, which, leaving it in terms of pi, just gives us 9 pi. Last on the warm-up, question 4. You have to sketch the curve y equals x brackets x minus 2 all squared. So this is a cubic graph. The power of the x cubed, sorry, the coefficient of x cubed is positive. It's positive x cubed, so it's going to be a cubic with this characteristic shape going upwards. Because we've got a bracket squared, this tells us that this is going to be a repeated root where x is 2. So we have a repeated root at x equals 2. And here we see that if x is 0, this is going to make the function equal to 0. And so this bit here tells us that another root is where x equals 0. But it's not repeated because it doesn't have power squared, cubed, or anything like that. And so this graph is going to come up through 0, 0, come up through the origin. It's going to curve back down, like so. It's then going to bounce back up and go up like so. And so this point here, which I've been a bit naughty, I've actually missed the x-axis here. That's slightly slack of me, but hopefully you'll forgive me. So it goes through that point here, where x is 2, and goes through the origin. For part 2, show that the equation x brackets x minus 2 all squared equals 3 can be expressed like so. So what we're going to do here is just expand this out first of all. So we have x brackets x minus 2 all squared equals 3. The first thing I'm going to do is expand out x minus 2 all squared. So x minus 2 all squared, we're going to get x squared. We double the product of these two terms, so x multiplied by minus 2 is minus 2x. Double that to get minus 4x. Then minus 2 multiplied by minus 2 gives us positive 4, which equals 3. So all I've done here for this step is expanded out x minus 2 all squared. If we now multiply this by the x on the outside, we get x cubed minus 4x squared plus 4x equals 3. And then finally, if we subtract 3 from both sides, we arrive at what we wanted to arrive at, and we get x cubed minus 4x squared plus 4x minus 3 equals 0, which is what we wanted to show all along. So that concludes the warm-up. So we can now start having a look at some of these much harder, dare I say, worked examples involving solving trig equations with use of the cast diagram. So let's get down to business. So the first worked example, we're asked to solve the equation 2 sine squared theta plus sine theta minus 1 equals 0 in the interval of theta from 0 to 360. So the first thing I'm going to suggest we do here is to rewrite this equation simpler. So I'm just going to set up a bit of space within to solve this. So my suggestion here is to let sine theta just be known as s. And so if we do this, it just reads much simpler. So let sine theta equal s. Then what we have here is 2 lots of sine theta all squared, which is 2s squared plus s minus 1 equals 0. So not only does it read easier and is simpler to write, but it makes it much more apparent to us that what we're dealing with here is a hidden quadratic. This is a quadratic equation within sine theta. And so the first thing is to think, can we factorize this? And the answer here is actually yes, we can. So what we need to do is multiply the 2 and the minus 1 together to arrive at minus 2, but we have positive 1s. So what two values, whole numbers, multiply together to give minus 2 but add up to positive 1? And those two numbers are going to be positive 2 and negative 1. So we can rewrite this as 2s squared plus 2s minus s minus 1 equal to 0. Now, these first two terms we can factorise out a 2 and an s. So we have 2s, brackets s plus 1, and the minus s and minus 1 have a common factor of negative 1, so we can put a minus 1 on the outside, and again we get s plus 1 for a second time in brackets, all equaling 0. So the 2s and the minus 1 can form together to make their own bracket, so 2s minus 1 brackets s plus 1 equals 0. Therefore, we have two possibilities of what sine theta, or our s, needs to be. So either this bracket is going to be equal to 0, in other words, we're going to have that s is equal to a half, or the second possibility is that this bracket is equal to 0, which is when s is equal to minus 1. So we have two different cases to consider separately. So the first case to consider is the case where sine theta equals a half. So let's consider where sine theta is equal to a half and get the cast diagram up and ready. So I'm going to just draw on the big X here, going through the origin. So if s is a half, in other words where sine theta equals a half, we can work out the principal value of theta. So principal value, I'm just going to be lazy and say PV. That's going to be sine minus 1 of a half. Now this is one of these exact trig values. So if we do sine minus 1 of a half, if you forgot what this is, it's okay, because we can just check it now. Inverse sine of a half is 30. So we worked out the acute angle in between this x-axis and these lines making the x. So we may as well just label this on. Next we can see here sine theta needs to be positive half in this case. And so where is the sine function positive? Well, it's positive here, because a for all trig functions are positive here, and it's also positive in the s quadrant. And so we can either have it where the value of theta is 30, which is this one. So we can have theta equaling 30 degrees, or as well, what we could have is theta over here. Now this angle here is 180 minus 30. This one's 150 degrees. So we can have theta being 30 or 150. The second thing to consider is, what if sine theta wasn't a half? What if sine theta was minus 1? So that's going to give us some more options. So if sine theta were minus 1, whereabouts on this cast diagram would that be? So let's just work out the principal value again in this case. So the principal value this time is sine minus 1 of negative 1. So if we try this, so shift sine minus 1, we get minus 90. So negative 90. Angles that are negative are measured clockwise from the positive x-axis. So minus 90 is going to be here. So it's going to straddle the t and the c quadrants. So we want our values of theta in the range from 0 to 360. So minus 90 isn't valid. So what value of theta would be valid? Well, rather than having a negative angle, what we could have done to arrive at this point here would have been to have gone all the way around in the positive direction, which would be positive 270. And that's the only valid solution for where sine theta is equal to negative 1. Sine theta is only going to be equal to negative 1 once every 360 degree repetition of the sine function. So every 360 degrees on, it will be minus 1 again. So there's only going to be one value here, 270, yet two values here for theta, the case where sine theta is a half. And so what we do now is we put together these two cases to form the overall solution. So this is the first case. This is the second case. So our valid values of theta are that theta is 30 degrees, theta is 150, or where theta is 270. So these questions require much more thought than the more basic ones. I'm going to also show you the power of graph software, for example Desmos, which has an app, or GeoGebra. So you could use a graph plotter to work these solutions out, to double check your answers, to make sure that when you're doing these at home, you've not missed any of these solutions out. For example, it's possible you got one or two but missed out a third one. It's imperative that you get all three valid solutions for theta to get full marks. So I'm going to show you how you could have plotted this on Desmos, which is just my own preference. So Desmos does freak out a bit if you just type in this equation as it is. The best thing to do is look at the left-hand side. Instead of using theta, plot x, because it defaults to having x and y. I've labelled this theta, but it actually thinks it's the x-axis, which is fine. And so just set the left equal to y, and the right-hand side of the equation, 0, set that equal to y as well. So you plot two different functions, essentially, and where they intersect, that corresponds to the solutions to the equation you wish to solve, which I've highlighted here in this blue colour. So this red wave here is 2 sine squared plus sine theta minus 1. And this horizontal blue line is just where y is equal to 0. So the intersections relate to the solutions, like I've said, so 30, 150 and 270. Any other intersections are outside this range from 0 to 360. So that's all we need to do for question 1. Let's have a look now at question 2. Question 2, we're asked to solve the equation 4 cos squared of theta minus 20 degrees equals 1, again in the same range for theta. So let's get the space ready to go, and let's first of all make a substitution for what's inside this bracket here. So what we need to do to make it just easier to read and easier to process is make a substitution here of big X. So let's have big X equal to theta minus 20. Now this is going to have a few implications here. If big X equals theta minus 20, that changes the limits on what we're looking for big X to be. So for theta, we want theta between 0 and 360. But if big X is whatever theta can be with 20 knocked off, we knock off 20 from this lower limit and the upper limit too. So the lower limit for big X is 0 minus 20, which is obviously minus 20. And the upper limit will be 360 minus 20, which will be 340. And it's worth just noting what theta is in terms of X. So if we say big X is theta minus 20, then fairly obviously theta is going to be big X plus 20. So I'm just going to let this hang above and to the side. We can return to this and remind ourselves later. Next, let's think about solving this. Now we're letting big X equal theta minus 20. So I'm going to substitute this in with big X. So this now becomes 4 lots of cos x all squared. So 4 cos squared x equals 1. Divide both sides by 4, we get cos squared big X equals a quarter. Then if we square root both sides, we then see that cos x is either going to be plus or minus the square root of a quarter, which is a half. So again, we need to consider both options here of cos x being negative a half, and also if cos x is positive a half. So let's consider each scenario in turn. So first of all, let's think about if cos x were positive 1/2. So again, get your cast diagram ready, do the big X going through the origin, and get the calculator to hand. And so what's the principal value if cos of x is a half? So what we actually need to consider here, and this is me making an honest mistake, I'm not going to lie to you, this isn't a mistake. What I need to do here is consider this to be x, not theta, but x. So I'll leave this mistake in. Whoopsie-daisy, I do apologise. So cos big X equals a half, because we've changed it from theta to x here. So let's get the calculator to hand and do inverse cos of 1/2. So shift cos 0.5, I'm just going to do, same as a half. We get 60. So that shows us that the principal value is that x equals 60. So we can label this on our cast diagram. Now, if cos of big X is positive a half, we now need to consider in which quadrants it's allowed to be in. So whereabouts is cos a positive function? Well, cos is positive in the A quadrant here. It's also positive in the C quadrant down here. Now, the range for big X we're requiring is from -20 up to 340. And so 60 is valid, so we can have 60, that's fine. So we can have big X being 60, which is allowed. We could also have it where big X is greater than this. So big X being 60 is fine. But if we go all the way around to the C quadrant in the positive direction, which is anti-clockwise, 90, 180, 270, this would be 300. It's almost a full circle, but without that 60. So big X can be 60 or 300. However, we actually want this answer in terms of theta, don't we? So just remind yourself that theta is x plus 20. And so now what we need to do is just add 20 to each of these values of big X. So theta is either 80 degrees or 320. So those are the two solutions for the possibility where cos of big X equals 1/2. So what now if cos of big X was this -1/2? What now? So let's think about this. Again, that should read big X. I'm just going to quickly change this. So again, my apologies to you. Just bear with me as I just craftily pencil over here. Okay. So again, with a cast diagram, we do the big X centered on the origin and use a calculator to work out the principal value of the variable, which in this case is big X, because we made this initial substitution of big X instead of this thing here. So shift cos -1. Now I'm just going to say -1/2. And we end up with 120. And so the principal value in this case is big X is 120. So cos is negative in the sine quadrant because only sine is positive there, and cos is negative in the t quadrant, again because only tan is positive there. So 120 if that's 120, which is valid because it's in the range of -20 to 340, if this is 120, this angle here again will be 60. So we can label in these acute angles on the cast diagram. So x being 120 is valid. We can have that one, that's fine. The other area where cos would be -1/2 is here. And so if these acute angles are 60, for this angle I'm drawing in with the red pen, this will be 180 plus 60, which will be 240. So it's tempting to stop there and think you've done all the hard work, but just remember, we're wanting an answer in terms of theta. So again, reminding ourselves that theta is x plus 20, we add 20 onto both of these values, then we see there that theta must be 120 plus 20, which must be 140, or 240 plus 20, which is 260. So the first scenario where cos x is positive, we have these solutions for theta. The second scenario where cos x is -1/2, we have these solutions for theta. So finally, we've put these together to arrive at our final answer. So therefore we have that theta equals 80, 140, doing them in order of size here. You don't have to, but I think it's a good idea to just do this. 260, and 320. So those are the solutions to this. 80, 140, 260 and 320. And again, just to show you using the graphing software, if you plot one function, 4 cos squared of x minus 20 equal to y, then a second function which relates to the right hand side of the equation you want to solve, just put 1 equal to y, see where the two graphs intersect, and these relate to the solutions we mentioned before. So as you can see here, highlighted in blue, 80, 140, 260 and 320. Question 3, we need to find all values of theta to one decimal place, just note that, in the interval from 0 to 360 for which tan theta squared, written as tan squared theta of course, equals 4. So easy to work out what tan theta needs to be just by square rooting both sides. So if we have tan squared theta equals 4, if we square root both sides, we can fairly easily see that tan theta is either going to be plus 2 or minus 2. So again, you might be getting used to this idea now. You need to consider more than one scenario. So the first scenario is where tan theta is going to be positive 2. So where would tan theta be a positive 2 here? So again, get your cast diagram ready, do a big X going through the origin, and work out the principal value on your calculator of where tan theta equals 2. So all we need to do here is just do tan minus 1 of 2. So shift tan 2 and give it to one decimal place. You get 63.4. So that's the principal value. So tan minus 1 of 2. We had 63.4. So we can label this on the cast diagram to make it a bit easier for us. So all of these acute angles in between the x-axis and the lines of the x are 63.4. So if tan theta is going to be positive 2, we just need to now consider in which quadrants tan is a positive function. Well, tan is positive in the A quadrant because all of sine, cos and tan are positive here, and tan is also positive in the T quadrant, quite obviously. And so in the range of 0 to 360, 63.4 is valid, so we can write this down. So therefore we can have theta being equal to 63.4, that's fair enough. So that one's relating to 63.4. Or we could have tan where theta is over here. So this is 180 plus 63.4. 180 plus 63.4. This red one here would be 243.4 degrees. So they're the two possibilities of where tan theta is a positive function. If we go on and added another 180, we're going to be outside of a range. So we've got them all here. The second thing is case 2, if tan theta happened to be minus 2. So again, cast diagram, this is going to be very similar to this one we've just done. So again, do the big X and work out the principal value by using the calculator and doing shift tan of minus 2. So I'm just going to keep that 2 here, input a minus in front, You can see here we get minus 63.4 degrees. So that's a principal value here. So just write this in, principal value, whoops. Principal value of theta is tan minus 1 of minus 2, which came out to be negative 63.4. Now this principal value isn't in the accepted range. The accepted range here is starting from 0 up to 360. So minus 63.4 is actually down here, which is not in range. Again, the size, the magnitude of this angle is 63.4, so I can label this in, that's okay. And we want tan to be negative, so just be considering in which quadrants is tan a negative function. Tan is positive in A and T, therefore tan is going to be negative in the sine quadrant and the C quadrant. And so in the range from 0 to 360, we're after this angle here. This angle here is going to be 180 minus 63.4. So if we just try that, 180 minus 63.4. We get 116.6, so that's one possibility for theta. Or we could go further around into this C quadrant. So if I just get the, oops, didn't want green, I wanted red. Must be going slightly blind. So go all the way around in the positive direction to C. So this is almost 360, just without this final 63.4. So 360 minus 63.4. That will give us a value of theta here of 296.6. So once again, we have two different scenarios to consider. The first one from case 1 is these values of theta. The other two cases from case 2 are these values of theta. We put them together into one to arrive at the full solution for what theta can be. So therefore theta is allowed to be 63.4 degrees, 116.6, 243.4, and the largest one, still in the range, is 296.6. So as I say, we get the overall solution by just combining these two into one. And again, looking at the graph from Desmos, plot tan squared of x equals y, and then plot 4 equals y, and see where it intersects. So in the range from 0 up to, but not going beyond 360, there's 4 points of intersection here, which correspond to the aforementioned 4 solutions for theta. And that's it for question 3, really. So we can now have a look at question 4. Question 4, we need to solve the equation cos theta brackets sine theta minus 3 cos theta equals 0 in the interval from 0 to 720. So just be careful, the interval isn't always from 0 to 360. So we need to give the answers to 3 significant figures for this one. So here, it's just worth noting that the interval is different, and as well, how to read this is something in itself. So this means cos theta multiplied by sine theta minus 3 cos theta. So just think of this as being a multiplication sign. It should be fairly obvious, but because you've not seen something like this before, perhaps, it is one function multiplied by this here. And so now you know that, it's actually easy to understand what you need to do. Doing it is a different question altogether. But what this means here is if we've got a compound function here equal to 0, either cos theta has to be equal to 0, because 0 multiplied by the bracket would give 0, or it could be that this stuff in the bracket is equal to 0. So those are our two cases to consider. So what we need to do now is first of all think about where cos of theta is equal to 0. So let's get the cast diagram ready. Here it is going to fly in. So again, we need to just work out the principal value. So what's the principal value that would give us the value of cos theta equaling 0? And we do this by just simply doing inverse cos of 0. If you can't picture the graph of cosine, just use the calculator, that's acceptable. So shift cos of 0, we get 90 degrees. Now 90 is in range, so that's absolutely fine, but this is a bit tricky. I just need to explain this to you. So 90 degrees would be right on the boundary between the A quadrant and the S quadrant. And it's tempting to think that that's going to be the only possibility of where cosine of theta is 0, but actually it isn't. So this is where thinking about the graph of cosine would be useful. Cos theta equals 0 every 180 degrees, not every 360, but every 180. And so there's also going to be a solution down here as well. I'm going to explain this in a different way, so hopefully it makes sense. So just think about the sign of the cosine function. In the A quadrant it's positive. In the S quadrant, only sine's positive, so cosine's negative here. In the tan quadrant, only tan's positive, therefore sine and cosine is negative. And obviously in the cosine quadrant, cosine is positive. So think about what 0 is. 0 is a boundary as we move from positive to negative. And so it stands to reason that this one here will relate to a value of cos theta equaling 0, because we're moving from positive to negative. 0 is the boundary. And in the same way, as we move from negative back into positive, the boundary from moving from negative to positive is again 0. And so this is a bit of a naughty question. It's very easy to think about only this option and not this one down here. But cos theta would equal 0 for this angle of theta, which is 90, but also this angle down here, which is 270. So therefore, in this range, theta could be 90, or it could be 270 as well. So 90 is the angle I drew in blue, which is the principal value the calculator gives us, or it could be 270. But the range here goes up to 720, so we need to carry on. So if you went around again, another 180 would go back to this one. So add 360 to both of these. 90 plus 360, the next value in range would be 450. And 270 plus 360 would be 630. If we added 360 to this one, we'd be outside of the range. And so these are all the values valid for theta for the first scenario, where cos of theta is 0. We now move on to thinking about the second case, where sine theta minus 3 cos theta is 0. So again, just get the cast diagram up and ready. Now this one needs a bit of rearrangement. So what we need to do first of all is to add 3 cos theta to both sides. So that gives us sine theta equals 3 cos theta. Now we can't really solve this with what we know, because we've got a mix of two different trig functions. We need to reduce it from 2 down to 1. So if we divide both sides by cos theta, we get sine theta over cos theta equals 3. But we now need to remember but this is an important identity. Sine over cos is the same as tan theta. So in other words, we're wanting to solve where tan theta is equal to 3. So we need to find the principal value for this. Principal value is tan minus 1 of 3. So shift tan minus 1. And for this one, we get 71.6 to 3 significant figures, which the question wants us to give. 71.6 degrees. So again, just add this to the cast diagram. Like so. Now 71.6 is within the range from 0 to 720, so that's absolutely fine. So we can label on 71.6 because that's all of the acute angles in between the x-axis and these lines making the x. And this will help us to solve for the other valid values of theta. So 71.6, that's allowed. So I'll add this in. So tan theta equaling 3. 3 is obviously a positive value. So whereabouts is the tan function positive? It's positive here in the A quadrant. It's also going to be positive in the T quadrant, where only tan is positive. So 71.6, we've got that one from the calculator. The next one would be this one plus 180 degrees. So all the way along to there. This one would be 180 plus 71.6. Now this one, 180 plus 71.6, that's going to be 251.6. Now that's 4 sig figs, not 3, but we can come to that later on. Now the tan function is periodic and repeats every 180 degrees. So this will go up in multiples of 180. So if we just keep on adding 180 until we get to the limits of the range, this one plus 180 is going to be 431.6. And add another 180 gives us 611.6. If we added another 180, we'd be beyond 720, and so this actually is all of them. So now we put these two bits together. So therefore, the valid solutions for theta, the smallest one is 71.6. Next up we have 90. After 90 we had 251.6, but to 3 sig figs this one will be 252. I don't really think the examiner is going to be too bothered if you just wrote 151.6. I don't think they'd mark you down, but do try and follow the rules of a question, what it asks you to do, to the absolute T, if you possibly can. So 3 sig figs, do what it says. The next one after 252 is 270. After 270 we have 431.6. To 3 sig figs this is 432. Then 450. Then 612 to 3 sig figs. And finally 630. Question 5. This one was a past exam paper question. So first of all we need to show that the equation 3 sine squared x plus 7 sine x equals cos squared x minus 4 is one and the same thing as 4 sine squared x plus 7 sine x plus 3 equals 0. Now, to make this just easier to write and just read a bit neater, the first thing I'm going to suggest we can do is just say that we're going to let small s denote sine x, and also we're going to say that little c denotes cos x. This is just going to make things easier to write down. So we start off with this one. So this one written in this shorthand way, which is absolutely fine. The examiner will not mind this at all. It's going to be 3 lots of s squared plus 7s equals c squared minus 4. Now again, a big clue here is we've gone from 2 different trig functions, sine and cos, and reduced it down to just being in terms of sine and sine squared. So what's happened here is this cos squared has basically vanished and been replaced with something related to sine. So how does cos squared relate to sine, or indeed sine squared? We need to remember this identity here, that sine squared plus cos squared is always equal to 1. So in other words, from that, cos squared is always going to be 1 minus sine squared. So 3 sine squared plus 7 lots of sine, that's going to be the same as 1 minus sine squared minus 4. Because, like I said there, cos squared is one and the same thing as 1 minus sine squared. And so this can then be rearranged. So if we add sine squared to both sides, we get 4 sine squared plus 7 lots of sine equals 1 minus 4. 1 minus 4 is minus 3. So 4 sine squared plus 7 lots of sine, add 3 to both sides now, plus 3 equals 0. Now this here is the exact same thing as this, but just written shorthand. So this is the same as what I've written here. So it's not a bad thing to just conclude and state what wanted to be proven. So therefore, 3 sine squared x plus 7 sine x plus cos squared x minus 4 becomes 4 sine squared x plus 7 sine x plus 3 equals 0. And we're going to use this result to solve the trigonometric equation in part B. So part B, the big word here is hence, so we're going to use part A to help us. We're solving in the region of x being from 0 to 360, this equation here, giving the answers to 1 decimal place where appropriate. So just giving ourselves a bit more space to solve this, what we had from earlier, this thing here, just going back 1 step, this thing here we said was actually the same as 4 sine squared plus 7 lots of sine plus 3 equaling 0. So we're going to be actually solving this thing here. So I'm going to just nab this, as it were. I'm going to copy that, and that's going to be what we're going to be solving here. Well, that didn't work. Never mind. Whoops-a-daisy. So anyway, I'll just do it the long way then. And so what we're going to try and solve here, rather than have this, we're after solving where 4s squared plus 7s plus 3 equals 0. And we got that from part A. So I'm just going to put in brackets, we got that from part A. So this here is a quadratic involving sine x. So this will factorise. So we can use the AC method, multiply the 4 by the 3 to get 12. So can we think of two numbers that multiply to 12 and add to 7? Hopefully we can. Those numbers are 4 and 3. So we can partition this 7s into a positive 4s and a positive 3s. We can now factorise this into two parts. So these two terms have a common factor of 4s. So we get 4s brackets s plus 1. These two have a common factor of 3. So we're going to get plus 3 lots of s plus 1 equals 0. We can now put the 4s and the positive 3 into their own bracket to arrive at 4s plus 3 brackets s plus 1 equals 0. So therefore, we've got two scenarios again to consider. So therefore, from this, we can see that either s, for this to be equal to 0, s would have to be minus 3/4, or this bracket might be equal to 0, in which case s would be negative 1. So let's consider these two scenarios in turn. So the first scenario we can look at here is the scenario where sine theta is negative 3/4. So let's consider this one first of all. So let's add the big X to the cast diagram, which we have here as ever. So we need the principal value of where sine x is equal to minus 3/4. So just using the calculator, we just do inverse sine minus 3/4. So shift sine minus 3/4. And bear in mind we need this to one decimal place as well. So here we get minus 48.6 to one decimal place. So we can write that down as our principal value. So x equals sine minus 1 of minus 3/4, and we got minus 48.6. Now, the range we're interested in here is from 0 to 360, so minus 48.6 is not in range. But the principal value, as ever, is still useful information. So what we could do with having is a positive value of theta. First off though here, we're wanting where sine is negative. So think about which quadrants sine's going to be negative in. Sine's going to be negative, not in this quadrant or in the sine quadrant, but in the t quadrant and in the cosine quadrant. And so even though we can't get to here by going negative because it's not in range, what we can do is go all the way around to here and around to this one as well. So the first valid value of theta is this one. Now this one in blue is 180 plus 48.6, which will be 228.6. This one here, going all the way around, almost 360, but just without this 48.6. So this one will be 360 minus 48.6. If you check that on a calculator, it'll be 311.4. So those are the two values we get from this scenario. It could, however, be where sine theta is negative 1. So this is our second case to consider. So over here, we have this. So where is sine of x going to be negative 1? So again, cast diagram, and find the principal value by doing inverse sine of minus 1. So here we get minus 90. So our principal value is negative 90. So x, we did sine minus 1 of minus 1 and got minus 90. Now that isn't in range because we want it to be between 0 and 360. But minus 90 would be down here, where again we're straddling, if you like, the boundary in between t and c. So sine of x is only going to be minus 1 at this one point here. So we want x to be a positive angle, and so it's going to be 270. 90, 180, 270. So therefore here theta is 270. So if we put these three values of theta into 1 to get our full overall solution, that's going to complete question 5 for us. So therefore, we're going to have theta being 228.6, 270. It's not appropriate to give this to one decimal place. And this one 311.4. So those are the three possible values of theta. So that's question 5 complete. So now, to finish off, we're going to have a look at question 6, which I've made deliberately to be absolutely fiendish. So brace yourself for question 6. Here it comes now. This final worked example, question 6, like I've said earlier, I created it myself, and it's made to be as hard as possible whilst not technically going beyond the scope of what's been taught so far, but it's putting it all together now. So what we need to do here is solve the equation 8 sine squared of 2 theta plus 30 minus 2 lots of 2 theta plus 30 equals 5. And again, I've made this interval slightly harder. Rather than it being from 0 to 360, I've made it from 360 to 720. So the question here is where to begin. You've got here two different types of trig functions, sine and cos, and as well as that, it's not just sine of a simple angle or cos of a simple angle, it's sine and cos of 2 theta plus 30. So it needs a lot of simplifying. So the first step, I would suggest, is that we say to allow 2 theta plus 30 to be big X. So let x equal 2 theta plus 30. Now this is going to change the limits. So the limits of theta are from 360 to 720. So let's think about what the limits of big X will be. So if theta is from 360 to 720, then 2 theta, we just double those limits. So 2 theta will be from 720 to 1440. And then if we add 30 onto each of these limits to get the limits of what 2 theta plus 30 would have to be, then add 30 onto here, we get 750. Add 30 onto here, you'll see we get 1470. So those are the limits of 2 theta plus 30. But because 2 theta plus 30 is x, then what we're saying here is that big X is going to go from 750 all the way up to 1470. So by making this substitution of big X being 2 theta plus 30, this does simplify things to quite a big extent. So by letting this substitution take place, this equation above becomes 8 sine squared big X minus 2 cos big X equals 5. But again, sine squared x and cos x still looks quite ugly, so we can go one step further and make other substitutions just to, if nothing else, make writing the equation easier. So next what I'd suggest we do is we let sine big X be denoted by little s and cos big X be denoted by c. And if we do that, 8 sine squared x we can write as 8 s squared, minus 2 lots of cos big X we can write as minus 2 lots of little c, equals 5. We now need to remember one of the important trig identities which we've seen before quite a few times, which relates sine squared and cos squared. So we need to remember rather, that sine squared plus cos squared is always equal to 1. So what we can do here is we can replace the sine squared and replace it with cos squared, because cos squared, just rearranging this here, is 1 minus sine squared. So using that, we can say that 8 lots of sine squared is the same as 8 lots of, so cos squared is 1 minus sine squared. We can say that sine squared is 1 minus cos squared too. So actually, we're going to be using this one here. So we're going to replace s squared with 1 minus cos squared. So 8 lots of sine squared is the same as 8 lots of 1 minus cos squared minus 2c equals 5. As I say, just replacing sine squared with 1 minus cos squared by using that trig identity. So next we need to expand this out. 8 times 1 is 8. 8 times minus cos squared is minus 8 cos squared. And minus 2c equals 5. This is essentially now a hidden quadratic involving cos big X. Now it's harder to solve when you've got the quadratic term as negative. So what I'm going to suggest we do here is multiply both sides of this equation by negative 1. What that will give us is positive 8c squared, positive 2c. This positive 8 becomes negative 8, and this 5 multiplied by minus 1 becomes minus 5. So if we add 5 to both sides, we then see that 8 lots of c squared plus 2c, then minus 8 plus this 5 becomes minus 3. That equals 0. Now this luckily will factorise, so we need to think of two numbers which when we multiply them together we get minus 24, and when we add them we get positive 2. So those numbers are going to be positive 6 and negative 4. So what this means is we can partition this 2c into a positive 6c and a negative 4c. So these two terms will factorise. We've got a common factor of 2 and c, so we can say this is the same as 2c brackets 4c plus 3. And these last two terms have a common factor of negative 1. So again we can factorise out the 4c plus 3 into this bracket, and that equals 0. So now this 2c and minus 1 can go inside its own bracket. So we have 2c minus 1 brackets 4c plus 3 equals 0. So now what we're going to have is two options for what cos of big X can be. And so this bracket might equal 0, in which case either C is a half, or from this bracket, for this bracket to be equal to 0, we see here that C would have to be negative 3/4. So in other words, either cos of big X equals a half, or we're going to have that cos of big X is negative 3/4. And so these are the two scenarios we need to consider in turn to get our full solution. So we're halfway there now. We've worked out what cos of big X needs to be, either half or minus 3/4. The next step is seeing what values of theta would give us what we need. So moving forward, considering both of these scenarios one by one, then here's what we have. So case 1, cos x is positive half. Case 2, cos big X is negative 3/4. So let's consider these one by one with, as you could probably guess by now, the cast diagram. So here's the first one. So cos of big X equaling a half. This is one of those exact trig ratios, but if you're not sure, please do use your calculator to find out what big X needs to be. So if we do shift cos minus 1 of 1/2, we see here that X, big X, needs to be 60. So that's our principal value. So we can add this onto our diagram. So the principal value here is that X is cos minus 1 of 1/2, which gives us 60 degrees. Now, just remembering from before what the range of big X was, the range of big X is from 750 at one end all the way up to 720 doubled, and then add 30. So the higher end is 1470. So that's worth recalling from the previous page. So 60 is in the range. So 60 is one of those allowed values, but it's not going to be the only one. So what am I talking about? 60 is not, so 60 is, it needs to be between 750 and 1470. So 60 is obviously far too low. Don't know what I was talking about there. So yeah, we need to be careful in terms of what values of big X we actually select to write down for our answer. It needs to be in this range here, let alone thinking about what theta is after. But we do know what the angle between these X lines and the X-axis is. It's going to be 60 degrees based on this principal value here. Now, cos of big X being a half is a positive value. So we need to think about now, using this cast diagram, where cos is a positive function. So cos is going to be positive here and here. And so we need to think about what values of X would be in the range. So one value is 60, which isn't in the range we need, but I'm going to write it down here, regardless. Another value of big X, which would give us cos X being a half, would be this one down here, and this one would be an angle of 300. Again, that's not in the range. So what we do now is we carry on. We need to remember that the period of the cos function is 360. So these values repeat every 360 degrees. So we add 360 onto this one, add 360 onto this one, until we eventually get values in the required range. And so 60 plus 360 is 420. This one plus 360 is 660. And as you can see here, still not high enough by any stretch. So go again. Add 360 onto this one. 420 plus 360, that's going to give us 780. Now that is in range. This one plus 360 gives us 1020. Can we go higher? In fact, we can. So add 360 onto each of these. So 780 plus 360, that gives us 1140. 1020 plus 360 gives us 1380. If we add 360 onto this one, we go up to 1500, which is outside of the range we need for big X. Remember, our big X needs to be in this range, and so the values we're going to consider here are these four. These are too low. These are lower than 750. This one here is higher than 1470. So these are the values of big X which we're going to consider. Next, we need to think about the second case where cos of big X is negative 3/4. So here's the cast diagram for this one. So again, to find the principal value, we're going to do cos minus 1 of negative 3/4. So shift cos minus 3/4. And we're going to give this to 1 decimal place, I'll say. 1 decimal place is fairly reasonable. So to 1 decimal place, this is 138.6. So this principal value is x was cos minus 1 minus 3/4, which came out to be 138.6. That's not in the required range. It's not to say it's not helpful though. So again, just doing our cast diagram, putting in the big X here. So one angle we've got is 138.6, which will be somewhere here. So if that's 138.6, we need to think about what the acute angle here would be in between the x-axis and these x lines. So we can work out this by doing 180 minus 138.6. So if we do this now, 180 subtract 138.6 gives us to 1 decimal place 41.4 degrees. And so we can fill this in as well. Next up, we need to consider where else the cosine function would be negative, because we want here cosine of big X being negative 3/4. And so cosine is negative in the S quadrant and the T quadrant. And so the principal value is one of those answers, 138.6. The other one is going to be 180 plus 41.4, and that one is going to be 221.4. And again, that isn't in the range we want, but regardless, we're going to start with these. So we had 138.6, 221.4. Now both of those are evidently far too small. We want at least 750. Remembering that cos is periodic and repeats every 360, the values of cosine of whatever, we simply add 360 onto both of those until we get values within the range required, similar to what we did earlier. So using your calculator, if we, to make sure you don't make any mistakes obviously, if we add 360 onto both of these, the next values we get are 498.6, and from 221.4 we get 581.4. Both of those are still too small. So if we add 360 onto both of these, 498.6 plus another 360, that gives us 858.6. Now that is in range. Add 360 onto this one, we get 941.4. I've worked these out in advance, so you can rest assured I'm not making any stupid slip-ups here. Keep going, add 360 onto both of these. What we get next is 1218.6. Add 360 rather onto this one here, and we'd get 13. So add 360 onto this one, I mean to say, we'd get 1301.4. Now, if we added 360 onto this one here, we get 1578.6, which is too large, and so we can stop. So all the ones in this required range, from 750 to 1470, are these ones I'm just going to highlight here. Okay, so we're nearly good to go now. So what we're going to do is write down all the required values of big X. So the smallest one is 780. Next along we had 858.6. Next up 941.4. After that we had 1020 and 1140. After 1140, next one, which is the biggest, next biggest, is 1218.6. Then 1301.4. And finally the biggest, which is valid, is 1380. But we don't want big X, we want our answers in terms of theta. So our final answers are going to be on this very bottom line. So we've got what big X is allowed to be. It's all of these here. So how do we go from big X to theta? How do we go from this line to the actual final answer line, if you like? So this is where we need to remember what we defined big X to be. We defined, just remember for a second, we defined big X as 2 theta plus 30. So therefore, rearranging in terms of theta, theta is going to be big X minus 30 divided by 2. And so we can work out the necessary values of theta by knocking 30 off each of these and then halving. And so the rule here is we're going to minus 30, then we're going to divide by 2. So it's quite arduous, which is why I don't believe it'd ask you this in an exam, but this is the ultimate test, I think, of these cast diagrams. If you can do these, you don't need to worry about anything at all. So if you find this hard going, it's meant to be, okay? So don't worry too much. But this is the final step, thank heavens. So this one here, subtract 30, divide by 2. So 780 minus 30 is 750. Half that, the first value of theta we're wanting is 375. And carry on accordingly, subtracting 30 and dividing by 2. The next one we get is 414.3. After 414.3 we get 455.7. Then 495. 1140 minus 30 is 1110. Divided by 2 we get 555. This one we get 494.3 to 1 decimal place. This one 635.7. And finally 1380 minus 30 divided by 2, we get 675. And that finally is our answer to what the valid values of theta need to be. That's the full solution set. If that were in an exam, which I very much doubt it would be, that would be probably about 10 marks, okay? That's as hard as you could ever expect to get, and I don't think the examiner would be quite that cruel. But just showing you to finish off and reminding you of the use of Desmos, here's what you get on Desmos. Okay, if you plotted this bit equal to y, and the right-hand side of the valid equation equal to y, and seen where they intersect, these answers highlighted in blue are the solutions to that equation for theta. So now it's over to you to practice these to wrap up the chapter. So if you were to have a look please at page 220, these questions, try them all and pay particular attention to the examination type questions here, which are very much like what you might get in an exam. So do work hard on these, try and nail every single one of these questions and ask me if you're not sure how to do them. Please remember to subscribe if you can, I'd be very grateful. Keep listening to the videos, working hard in lessons, and you'll see me very soon, I should hope. Thanks for listening, and bye for now.